somewhere between the stars. A planet is moving without a sunrise. It may be larger than Jupiter, carrying the fading heat of its formation beneath bands of cloud. It may be a small rocky body wrapped in ice and marked by craters no daylight will ever reveal. Or it may belong to a class of worlds we have not yet imagined clearly, because nearly everything we know about planets begins with a star. A planet, in the familiar sense, has an orbit. It circles a sun. Its years are measured by returning seasons, and its surface is shaped by a steady relationship with light. But not every planet remains inside that arrangement. Some are thrown outward while their systems are young. Newborn planets can pull on one another, trading energy through repeated gravitational encounters until one world is driven into a wider orbit and another is expelled completely. A passing star may disturb a planetary system. A companion star may reshape it. In crowded regions where many suns are born close together, the pathways of young worlds can become unstable before their systems have fully settled. Once released, a planet does not stop moving. It continues along a new path through the Milky Way, held by the gravity of the galaxy rather than by a single parent star. It passes through the spaces between stellar systems, where the nearest sun may remain so distant that it appears as only another point among billions. Astronomers call these objects free-floating planets or rogue planets. The second name can make them sound restless or dangerous. In reality, there is no intention in their motion. They are following gravity, as every moon, comet, star, and galaxy does. Their journey is not a rebellion. It is the result of an earlier encounter, written into speed and direction. Some may never have belonged to a star at all. Objects with planetary masses can also form when small clouds of gas collapse on their own, through a process more like the birth of a star than the assembly of a planet inside a disk. This creates a difficult boundary. Two isolated worlds may have similar masses and temperatures, yet very different origins. One may have formed beside a star and later escaped. The other may have condensed alone from a cloud. From a great distance, those histories are not easy to separate. The worlds themselves are also difficult to find. A star announces its presence through light. A planet orbiting that star may reveal itself by dimming the starlight, tugging on the star, or reflecting a small portion of its glow. A free-floating world offers none of those regular signals. Older ones may emit very little heat. Rocky examples could be almost completely hidden against the background of space, and yet gravity can disclose what light does not. When an unseen planet passes almost exactly in front of a distant star, its gravity bends and concentrates the star's light for a brief time. The background star appears to brighten, even though neither object has produced any additional energy. The planet has acted as a natural lens. For a massive rogue world, that brightening may last for days. For a smaller one, it may persist for only hours. Then the alignment ends. The star returns to its former brightness, and the unseen planet continues onward. A single passing world can therefore be known through one temporary change. In a star, it may never approach again. These short events have suggested that wandering planets could form a large hidden population throughout the galaxy. Their exact numbers remain uncertain. Detecting them is difficult, and estimating their masses from brief lensing signals can require additional measurements. But the evidence is enough to show that planetary systems do not keep every world they create. The spaces between the stars are not empty. They contain gas, dust, radiation, small bodies, and planets moving on solitary galactic paths. Each carries a history of formation, disruption, or escape. Each raises the same question in a different form. What becomes of a planet after it loses its sun? To follow that question, we will begin where many of these worlds begin, inside young systems where gravity has not yet found its final arrangement. A planetary system begins as a crowded place. Before there are finished planets, there is a broad disk of gas and dust turning around a young star. Within that disk, grains collide and cling together. Small fragments become larger bodies. Larger bodies begin to gather material through gravity, and over millions of years, a family of worlds starts to take shape. From a distance, the process can sound orderly. A star forms at the center, planets grow around it. Each world settles into a stable orbit, and the system continues for billions of years. But the early stages are rarely so simple. Young planetary systems can contain more bodies than they will eventually keep. Their orbits may cross, their gravitational pulls overlap. A planet that seems secure for thousands of revolutions can slowly be pushed into a new path, then encounter another world closely enough for the entire arrangement to change. Gravity does not need a collision to reshape a system. When two planets pass near one another, each accelerates the other. The direction and strength of that exchange depend on their masses, their speeds, and the geometry of the encounter. One world may lose orbital energy and move closer to the star. The other may gain energy and travel outward. If the outward moving planet gains enough speed, the star can no longer hold it. There is no visible boundary where a solar system ends. No edge a planet crosses and suddenly becomes free. Instead, there is a gradual weakening of the star's influence. The farther a planet travels, the more slowly it moves along its orbit, and the more easily another encounter can alter its future. At a certain speed and distance, the path no longer curves back. The planet has escaped. This process is known as gravitational scattering, and it is one of the main ways astronomers think rogue planets are produced. It may be especially common during the first tens of millions of years after a star forms, when giant planets are still migrating and smaller bodies remain abundant. A massive planet can disturb an entire system. Jupiter-sized worlds have strong gravitational reach. If several of them form around the same star, their orbits may remain unstable for a long time. Each close approach changes their paths a little. Eventually, one encounter can become decisive. One planet may be pushed inward, another may be sent outward, a third may be removed completely. Computer models of young planetary systems often produce this kind of outcome. When several large planets begin in compact arrangements, many simulations end with fewer worlds than they started with. The surviving planets settle into wider or more eccentric orbits, while the others leave the system and continue through the galaxy. The same process can affect smaller planets. A rocky world does not need to be large to be ejected. It only needs to encounter a more massive neighbor under the right conditions. A close passage near a gas giant can change its velocity enough to send it into a distant orbit, and repeated passages can finish the escape. Some of these worlds may once have been warm. A planet ejected from the inner part of a system could have possessed oceans, an atmosphere, or active geology before its orbit began to change. Its departure would not happen because the planet had reached the end of its physical life. It would happen because the surrounding architecture had become unstable. The transformation could be gradual from the planet's point of view. At first, the parent star would still dominate the sky. The world might pass through a long, stretched orbit, spending part of each year near familiar warmth and the rest far away. Later encounters could widen that path further. The star would appear smaller, seasons would lengthen. The intervals between close returns would grow. Then, after a final encounter, there would be no return at all. The star would recede into the surrounding field of light, becoming less like a sun and more like one of the many distant points in the galaxy. The ejected planet would still carry the motion it had acquired inside the system. Its rotation would continue. Moons, if they remained gravitationally bound, could travel with it. An atmosphere might stay in place, depending on the planet's mass, temperature, and composition. Not everything would be stripped away. a large planet could retain much of its gaseous envelope. A rocky planet with a dense atmosphere might keep that atmosphere for a long time, though its upper layers would cool. A world with internal heat could remain geologically active beneath an increasingly frozen exterior. The departure from a star is therefore not the disappearance of a planet, it is a change in environment. Other events can create the same result. In a young star cluster, neighboring stars may pass relatively close to one another. Their gravity can disturb the outer regions of planetary systems, especially planets already traveling on wide orbits. A world that was only weakly bound may be pulled away or nudged into an escape path. Binary stars introduce another source of instability. A planet orbiting one member of a double star system must move within a changing gravitational landscape. Many such systems can support stable planets, but certain orbital arrangements are fragile. If a planet moves too far from one star, or if the two stars have a close and eccentric orbit, repeated disturbances can gradually increase the planet's chances of being expelled. Stellar evolution can also alter a system. As a star loses mass late in its life, the gravitational hold on its planets weakens. Their orbits expand. Worlds that were once separated by stable distances may begin to interact in new ways. Some may survive in broader orbits around the stellar remnant. Others may scatter or escape. A rogue planet can therefore be older than the event that made it rogue. It may spend billions of years inside a system before leaving. The galaxy may contain newly ejected worlds that still hold traces of their former warmth, and older ones whose surfaces have been frozen for ages. There may also be objects that never experienced ejection. In regions where stars are forming, small clumps of gas can collapse under their own gravity. If a clump does not gather enough mass to become a star, it may form a free-floating object with a mass similar to that of a giant planet. Astronomers sometimes call these planetary mass objects. Their existence complicates the meaning of the word planet. A Jupiter mass body formed inside a disk and later expelled may look very similar to a Jupiter mass body formed alone from a collapsing cloud. Their atmospheres may contain similar molecules. Their temperatures may overlap. Their light may reveal little about the circumstances of their birth. Origin, rather than appearance, becomes the hidden distinction. One object was built from material, orbiting a star. The other formed more like a very small star. Both now travel without a parent sun. This uncertainty is part of the challenge astronomers face. A free-floating object can be measured by its brightness, temperature, motion, and spectrum, but its history may remain difficult to reconstruct. Even when a wandering world is found, the path that brought it into isolation may no longer be visible. Yet every one of these objects carries evidence. Its mass may hint at how it formed. Its atmosphere may preserve chemical signs of its early environment. Its speed through the galaxy may connect it to a nearby stellar nursery or moving group. A surrounding disk or companion moon could suggest a young age. No single clue is always enough. The story is assembled slowly from motion, heat, chemistry, and probability. And before that story can be read, the world must first be found. That is where the difficulty deepens, because a planet without a star does not pass in front of a familiar sun, and it does not pull a visible host back and forth. Most of the time, it moves through the galaxy unseen. To find a planet that gives off almost no light, astronomers often watch a different star entirely. The star may lie thousands of light years beyond the wandering world. It does not belong to the planet, and the two objects may never come near one another in three-dimensional space. They only appear to meet because, for a brief interval, Earth, the unseen planet, and the distant star fall along nearly the same line of sight. During that alignment, gravity changes the path of the starlight. Einstein's theory of general relativity describes gravity not as an invisible rope pulling across space, but as a change in the geometry through which matter and light move. A massive object curves the space around it. When light passes through that curved region, its path bends. A planet produces only a small amount of curvature, but with the right alignment, the effect can be measured. Light from the background star travels toward Earth along more than one bent path. Those paths cannot usually be resolved as separate images because the angles involved are too small. Instead, their light combines, and the star appears brighter than it did before. This is gravitational microlensing. The star itself has not changed. It has not flared, grown hotter, or moved closer. The temporary brightening comes from the geometry between the source of the light, the lensing object, and the observer. As the planet moves across the line of sight, the brightness rises. It reaches a peak near the closest alignment. Then it falls again. The pattern is often smooth and nearly symmetrical, like a low hill appearing in a long record of starlight. Its duration depends on several things at once: the mass of the lens, its distance from Earth, the distance to the background star, and the speed at which the objects move across one another's apparent positions. A star can create a microlensing event lasting weeks or months. A planet produces a much shorter signal. For a free-floating world with a mass comparable to Jupiter, the brightening may last a day or two. Lower mass planets can create events measured in hours. At the smallest scales, the useful part of the signal may pass during a single night. This makes the search both simple in principle and demanding in practice. Astronomers do not need to see the planet. They do not need it to transit a host star or reflect sunlight. They only need to record the brightness of the background star before, during, and after the alignment. But they must be watching at the right time. Microlensing events cannot usually be predicted far in advance. The lens may be too faint to identify before it passes in front of the source. Once the brightening begins, telescopes must collect measurements frequently enough to preserve the shape of an event that may soon be over. And after it ends, the same alignment will almost certainly never return. The planet continues along its galactic path. The background star remains far behind it. Their brief arrangement separates, leaving only a series of brightness measurements stored in observatory archives. There may be no second orbit to wait for, no repeating transit, no seasonal return. A planet found through microlensing can announce itself once, then disappear from that particular experiment forever. For this reason, surveys observe crowded fields containing millions of stars at the same time. Many of these fields lie toward the central regions of the Milky Way, where distant stars appear densely packed across the sky. The greater the number of monitored stars, the greater the chance that one of them will temporarily align with an unseen object in the foreground. Each image records more points of light than a person could examine individually. Software measures the brightness of those stars again and again. It searches for changes that match the expected form of gravitational lensing while separating them from stellar variability, atmospheric effects, detector noise, and the overlap of nearby stars. Most stars do not brighten in the required way. Some vary because of processes within the stars themselves. Some are members of eclipsing binary systems. Some measurements are altered by weather, telescope movement, or changing background light. A possible microlensing event must be tested against these alternatives. When the signal is very short, the challenge becomes sharper. A handful of measurements may contain nearly everything known about the lens. A gap caused by daylight or clouds can remove the peak of the event. Observatories spread across different longitudes can help, passing the observation from one region of Earth to another as night moves around the planet. For a few hours, telescopes separated by oceans may watch the same distant star. One site sees the brightness beginning to rise, another records the peak, A third follows the return toward its normal level. Together, they assemble a continuous trace of an object none of them can see directly. Yet, even a clear microlensing curve does not automatically reveal the planet's mass. The duration alone is not enough. A nearby, low-mass object moving slowly can create an event similar in length to one produced by a more massive object farther away and moving faster. Mass, distance, and transverse motion are woven together in the signal. Astronomers call this a degeneracy. It means that several different physical situations can explain the same observed curve. The event can indicate that a compact object passed in front of the star, but additional information is often needed to determine exactly what that object was. One useful clue appears when the background star is not a perfect point. During an especially close alignment, the lens may pass across the apparent face of the source star. Different parts of that stellar disk are magnified by different amounts. The resulting deviations in the light curve allow astronomers to estimate the angular scale of the lensing geometry. Another clue comes from parallax. Observers at different locations do not view the alignment from precisely the same angle. Two separated telescopes may measure slight differences in the timing or shape of the event. The separation can be the width of Earth, or much larger if one observatory is in space. Those differences can help break the connection between mass and distance. Even then, uncertainty may remain. A short event can be caused by a true rogue planet, but it can also come from a planet moving in a very wide orbit around a star. If the host star is far enough from the planet in the projected image, its gravity may leave no obvious mark on the brief lensing curve. The event then looks isolated. Later observations may search for light from a possible host near the lens position. If no star is found, the case for a free-floating planet becomes stronger, but a small or faint host could remain hidden, and a very distant orbital companion may require years of careful imaging to rule out. For that reason, astronomers often use the term candidate. It preserves the distinction between what the data clearly show and what they only suggest. The signal may establish the presence of a planetary mass lens while leaving its full relationship to any star unresolved. This caution does not make the detection less meaningful. It reveals the kind of knowledge microlensing provides. Most methods begin with a visible star and ask what may be orbiting it. Microlensing begins with a temporary alteration of light and works backward toward an unseen mass. It can detect objects that would otherwise remain beyond the reach of reflected light, thermal imaging, or stellar wobble. It is especially valuable for worlds smaller than the glowing young giants that infrared surveys can find directly. A newly formed planet may still radiate enough heat to appear in a sensitive infrared image. Over time, it cools, its emission weakens, and the distance across which it can be detected becomes smaller. Gravity does not fade in the same way. An old planet can become cold and dark, but it continues to curve the space around it. Given a favorable alignment, that curvature can still brighten a distant star. A world that has traveled alone for billions of years may therefore be discovered not by anything it emits, but by what passes behind it. The event contains no photograph of a surface. There are no visible clouds, rings, continents, or moons. The planet may be known first as a duration, a curve, and a range of possible mass. Yet within that brief signal is a complete physical encounter between light and gravity. Photons leave a distant star. They cross a large portion of the galaxy, near Earth's line of sight. They pass an object that may have wandered since the youth of its original system. Their paths bend by a minute amount. Some arrive at a telescope that would otherwise have missed them. For a few hours, the star becomes brighter. Then the geometry opens again. The extra light fades, while the planet moves on without any awareness that its presence has been recorded. From such passing alignments, astronomers are beginning to estimate how many unbound worlds may inhabit the Milky Way? The answer remains uncertain, because a population glimpsed through rare and temporary events is difficult to count. But the events already reveal something important. Between the familiar systems marked by visible suns, gravity is carrying evidence of many more worlds. Microlensing finds worlds through gravity, but some wandering planets can also be found through the heat they have not yet lost. A young giant planet begins its life carrying energy from formation. As gas and dust collapse into a growing world, gravitation energy is converted into heat. Material falls inward, pressure rises, and the planet's interior becomes much warmer than the space around it. Even after the surrounding disk has dispersed, that stored energy continues to escape. The planet glows, not in visible light, as a star does, and not because of fusion in its core. Its radiation emerges mostly at infrared wavelengths, beyond what human eyes can see. To an infrared telescope, a recently formed free-floating planet may appear as a faint source, with a temperature, spectrum, and brightness that can be studied directly. This method favors youth. A massive planet, a few million years old, can remain warm enough to detect across considerable distances. The same planet, after several billion years, may be so cold and dim that it becomes nearly impossible to distinguish from the background. Time gradually closes the window. For this reason, many directly observed planetary mass objects have been found in or near young stellar associations. These are groups of stars born from the same broad region of gas, moving through the galaxy with related ages and motions. If a faint infrared source shares the motion of such a group, astronomers can estimate its age more confidently. Age matters because brightness alone does not reveal mass. A young, low-mass object may glow as brightly as an older, more massive one. Both can have similar temperatures, colors, and spectra. To decide whether the object lies in the planetary mass range, astronomers compare observations with models of how such bodies cool over time. Those models track the gradual release of internal energy. A newly formed object may contract as it cools, radiating more strongly in its youth. Later, the contraction slows. The outer atmosphere becomes colder. Different molecules become stable. Clouds form at different levels, and the spectrum changes. By combining age, luminosity, and temperature, researchers estimate mass. The result is not always exact. Formation history can affect the amount of heat a planet begins with. An object assembled through rapid collapse may start with a different internal energy than one built more gradually inside a planetary disk. Cloud structure, atmospheric composition, and gravity also influence the light that reaches a telescope. The same observed brightness can therefore correspond to more than one possible past. Still, infrared observations reveal something microlensing usually cannot. They reveal the atmosphere itself. The light emerging from a warm, free, floating object passes through layers of gas containing molecules that absorb particular wavelengths. When astronomers separate that light into a spectrum, dark and bright regions appear. These patterns act as chemical signatures. Water vapor may leave one set of features. Methane leaves another. Carbon monoxide, ammonia, and metal-bearing compounds can also shape the spectrum, depending on temperature and pressure. The atmosphere of a giant rogue planet is not a smooth shell with a single temperature. It is a deep environment in which pressure increases downward and heat moves outward from the interior. Clouds may form from materials unfamiliar in Earth's weather. At higher temperatures, mineral particles and droplets of molten compounds can condense in the atmosphere as the object cools. These clouds may sink beneath the visible layers. At lower temperatures, different species become important, including sulfides, salts, and eventually water-based clouds in the coldest cases. The appearance of the world changes as chemistry follows temperature. Young, warmer objects may show thick clouds that redden their infrared. Cooler ones can develop clearer upper atmospheres, allowing methane absorption to become more prominent at still lower temperatures. Additional compounds appear, and the emitted light shifts toward longer wavelengths. Astronomers organize many of these objects into spectral classes. The sequence begins with the coolest stars and continues into brown dwarfs and planetary mass bodies. The boundaries are not simple divisions between stars and planets. They describe how atmospheres look at different temperatures. An object in one class may have been born as a failed star. Another, with a similar spectrum, may have formed as a planet and later escaped. Their light can be alike because atmosphere responds strongly to present conditions, while origin is buried in the past. Brown dwarfs occupy the middle ground. They form in a star-like manner from collapsing gas, but they never gather enough mass to sustain ordinary hydrogen fusion. Some can briefly fuse deuterium, a heavier form of hydrogen, if they are massive enough. Others fall below that threshold. Below them are objects whose masses overlap with giant planets. The commonly used distinction near the deuterium burning limit is useful for classification, but nature does not place a visible marker there. An object just above the threshold and one just below it may look nearly identical. This creates a naming problem. Should a free-floating body with 5 times the mass of Jupiter be called a planet if it formed alone? Should a body with 15 Jupiter masses still be called a planet if it formed in a disk and was later ejected? Different astronomers emphasize different definitions. Some classify by mass, others by formation history. Some use broader terms, such as substellar object or planetary mass object. When the origin is uncertain, the disagreement is not only about words. It reflects a deeper difficulty in reconstructing formation from the object we see today. A world can lose its star and retain little direct evidence of the event. Its former orbit is gone. Its parent system may be far away. Its direction of travel may have been altered by later gravitational encounters. Even its atmosphere can evolve. Radiation from its original star may once have shaped the upper layers. After ejection, that influence disappears. The atmosphere cools toward a new balance, set mainly by internal heat and the weak background radiation of space. A large gas giant can remain warm inside for a very long time. Jupiter today emits more energy than it receives from the Sun. Its interior still holds heat from formation along with energy released. As the planet slowly contracts and separates elements within its deep layers, a free-floating giant could continue the same process without sunlight. At first, the loss of the star may matter little to the lower atmosphere. Internal heat already dominates there. Upper clouds would cool, but the deep interior would change more gradually. For some time, the planet might continue to produce weather. Heat rising from below can drive convection. Winds can redistribute energy. Clouds can form, dissolve, and reform. Storm systems may continue without any day-night cycle imposed by a nearby sun. There would be no illuminated hemisphere and no night side. Every location would receive nearly the same faint external light from the galaxy. Weather would be powered from beneath rather than above. The sky of such a world would depend on its atmosphere. A person cannot stand on the visible surface of a gas giant because no solid boundary separates the atmosphere from the deeper fluid layers. Descending through the clouds, pressure and temperature would increase until ordinary distinctions between gas and liquid became less useful. From high in the atmosphere, distant stars might be visible through clear regions, though clouds and haze could hide them. There would be no bright solar disk. The Milky Way might remain in the same broad sky for long intervals as the planet rotated. Constellations would rise and set according to the planet's spin, but none would dominate as a sun. Any moons could create additional motion. A giant planet expelled from a system may retain some satellites, especially those orbiting close to it. More distant moons would be easier to strip away during the gravitational encounter that caused the escape. The surviving moons would continue circling the planet. Their tides could shape one another's interiors. If several moons remained in resonant orbits, gravitational flexing might generate heat, as it does in parts of our own solar system. A moon could therefore possess two important sources of energy: heat from the planet when the system was young, tidal heating from its orbit, far from every star. Those sources might persist after sunlight had disappeared. The idea leads toward one of the more intriguing possibilities surrounding rogue planets, that a world can lose its sun without losing every environment where liquid water might exist. On the surface, the answer seems clear. Without starlight, an exposed ocean would cool, ice would form. The upper atmosphere might condense or collapse, depending on its composition and pressure. But a surface is only one layer of a planet. Below it, heat can remain. Rocky material contains radioactive elements that release energy as they decay. A planet also preserves heat from its formation and from the sinking of denser material toward its center. If it has a large moon or experiences internal tidal forces, additional energy may be generated. This heat moves outward through rock and ice. On Earth, geothermal energy is weak compared with sunlight, yet it is sufficient to maintain hydrothermal systems on the ocean floor. Around some icy moons, internal heat keeps water liquid beneath shells that never receive enough solar warmth to melt. A rogue planet could follow a related pattern on a larger scale. A thick layer of ice would insulate the water below. Ice conducts heat, but not instantly. If the layer became deep enough, pressure would rise, and different crystalline forms of ice could appear beneath the familiar surface ice. The arrangement would depend on the planet's mass, water content, and internal temperature. In some models, an ocean could remain between the upper ice shell and deeper high-pressure ice. In others, liquid water might touch rock, allowing chemical exchange between the ocean and the planet's interior. That contact matters for habitability. On Earth, interactions between water and rock provide minerals and chemical gradients that support ecosystems. Hydrothermal vents release heat and compounds into the deep ocean, creating environments that do not depend directly on sunlight. A starless ocean, if it existed, would not resemble Earth's surface seas. There would be no photosynthesis based on visible light. No sunrise would warm the upper water. Energy would enter from below, unevenly distributed around volcanic regions, fractures, and chemically active boundaries. The total energy could be limited. Life, if it arose or survived there, might remain sparse and slow-growing. Its possibilities would depend on chemistry, stability, and time, not merely on the presence of liquid water. Liquid water alone is not evidence of life. It is one condition among many. A rogue planet may also preserve surface warmth through an unusually thick atmosphere. Hydrogen is particularly effective in this context. Though a hydrogen atmosphere does not absorb visible light in the same way as common greenhouse gases, pressure-induced actions between hydrogen molecules can absorb infrared radiation. A sufficiently massive hydrogen envelope could trap internal heat. In theoretical models, a rocky planet with a dense atmosphere may maintain temperatures that allow liquid water at the surface. Even far from any star, the required conditions are demanding. The atmosphere would need to survive formation, ejection, cooling, and escape to space. Such a world would be unlike Earth. The pressure could be high, the atmosphere might be deep, the surface would receive little external light, and its climate would be governed by geothermal energy and the insulating effect of gas. But it would not necessarily be frozen solid. The possibility expands the range of places where stable liquid environments might occur. The habitable zone around a star is useful because it describes where surface water may persist under suitable atmospheric conditions. It does not describe every path to warmth. A rogue planet has no traditional habitable zone. Its potential environments are determined from the inside outward. Mass sets gravity. Gravity helps retain atmosphere. Composition sets opacity and chemistry. Radioactive elements and formation history shape internal heat. Moons and orbital resonances may add tides. Ice and gas determine how quickly energy escapes. Each world would carry its own thermal history. Some would freeze rapidly. Some would retain deep oceans. Some giant planets might remain luminous in the infrared for hundreds of millions of years, their weather gradually weakening as the interior cooled. Some smaller worlds could become dark almost at once on astronomical timescales, while preserving activity below the surface. A planet between the stars is therefore not defined by emptiness alone. It is a layered object moving through a cold environment, but carrying energy that began before its escape. The question is not whether the lost sunlight matters. It does. The question is how much of a world can continue after the sunlight is gone. To answer that more fully, we have to follow heat beneath the clouds and ice into places where the surface no longer tells the whole story. Beneath a frozen surface, time can move differently. The upper layers of a rogue planet may respond quickly to the loss of a star. Temperatures fall, water begins to freeze, gases may condense, escape, or settle into a new atmospheric balance. Far below, the response is slower. Heat trapped inside rock and metal does not vanish when the sky grows dark. It continues to move outward, crossing the interior through convection and conduction. Radioactive elements release energy as they decay. Donsin materials settle. The planet contracts by small amounts. Each process adds a little warmth to the deeper layers. On a world with enough water, ice begins to form from the top downward. At first, this seems like the end of an ocean. The surface hardens. The boundary between atmosphere and water becomes a lid. As the ice thickens, the remaining liquid is pushed farther from the exterior. But ice can also preserve what it covers. A frozen shell limits the rate at which heat escapes. The deeper water no longer touches the cold atmosphere directly. Energy from the interior accumulates beneath an insulating layer, and under the right conditions, part of the ocean can remain liquid for long periods. The balance is delicate. If internal heating is too weak, the ocean eventually freezes. If the ice shell conducts heat too efficiently, warmth escapes faster than it can be replaced. If the planet is large enough, contains sufficient radioactive material, and begins with enough internal energy, liquid water may persist much longer. The exact timescale depends on the world. A small rocky planet cools more quickly because it has more surface area relative to its volume. A larger one retains heat more effectively. Composition matters as well. Rock rich in radioactive elements can support more internal heating than rock with fewer of them. Water itself changes under pressure near the surface. Ice forms the familiar crystal structure found on Earth. Deeper down, where pressure becomes immense, water molecules can arrange themselves into denser forms of ice. These high-pressure phases do not need extreme cold. They exist because the weight above them forces the molecules into compact structures. On a water-rich rogue planet, the ocean may therefore be divided. An upper shell of ordinary ice could cover a liquid layer. Beneath that liquid, high-pressure ice might separate the ocean from the rocky interior. This separation would affect chemistry. If liquid water never touches rock, it may receive fewer minerals from below. Chemical reactions that depend on water moving through fractures in the crust would be limited. The ocean could still contain compounds inherited from the planet's formation, but its long-term chemical diversity might be reduced. On other worlds, the liquid layer may remain in direct contact with stone. That contact opens more possibilities. Water can react with minerals in the crust. Heat can drive circulation through cracks. Compounds can be carried upward from the interior and returned downward again. Over time, these processes create chemical differences between one region and another. Life on Earth depends not only on ingredients, but on gradients. A region rich in one chemical beside a region rich in another can provide usable energy. Hydrothermal systems on the ocean floor create such differences. Hot, mineral-rich water emerges from the crust and meets colder seawater, producing reactions that microorganisms can exploit. A rogue planet with an underground ocean might support similar activity. There is no reason to assume that it would. The pressure may be too high, the chemistry may be unsuitable, the ocean may be too stable, too isolated, or too poor in available energy. The interior may cool before complex chemistry has enough time to develop. But the absence of sunlight does not close every pathway. It changes which pathways remain. On Earth's surface, sunlight supports nearly all familiar ecosystems. Plants, algae, and photosynthetic microbes capture solar energy, and much of the rest of life depends on them directly or indirectly. Deep underground and at the bottom of the sea, there are communities with a different foundation. They use chemical energy. Some microorganisms gain energy from hydrogen, sulfur compounds, methane, iron, or other materials involved in reactions between water and rock. They do not need sunlight to perform these basic metabolic processes. This fact does not prove that hidden oceans on rogue planets contain life. It only shows that biology is not required to begin with daylight. The more difficult question is whether the necessary chemistry could originate and persist in isolation. A world ejected early from its system may cool before surface. Oceans have had much time to interact with an atmosphere and rocky crust. A world ejected later might carry a more developed chemical environment beneath its ice. Its history before escape could matter as much as its history after. Imagine a young planet forming within the warmer region of a planetary system. Water circulates on the surface. Volcanoes release gases. Impacts deliver additional material. The atmosphere, crust, and ocean exchange chemicals for millions of years. Then gravitational encounters shift the orbit. The star grows smaller in the sky. Survey water freezes. The atmosphere changes. Yet beneath the new ice shell, some of the original ocean remains. In that case, the planet would not begin its starless journey as an empty frozen body. It would carry an active chemical past into a new environment. Another planet may form farther out, where ice was abundant from the beginning. It could assemble with a deep water layer and a rocky core, then be expelled before its system fully settled. Its ocean might melt later from internal heat, never having known a bright surface. Both worlds could become rogue planets with hidden water. But their internal chemistry would be different. One would preserve a former surface environment. The other would develop entirely beneath ice. Even their oceans might not remain global. Heat is rarely distributed evenly. Radioactive elements can be concentrated in certain layers. Mantle convection can produce regions of stronger upward flow. Tidal forces from a moon may flex one part of a planet more than another. Crustal thickness can vary. The result could be pockets of liquid beneath a largely frozen shell. There may be seas beneath thinner regions of ice, separated from one another by frozen barriers. Warmth could collect around volcanic provinces. Briny water might remain liquid at temperatures below the freezing point of pure water. Salts lower the temperature at which water freezes. Ammonia and other dissolved compounds can do the same. These substances may help maintain liquid layers, though they also change the chemistry and physical behavior of the ocean. A hidden sea on a rogue planet could therefore be cold, pressurized, salty, and chemically unlike any surface water on Earth. Above it, the ice shell might be several kilometers thick or much more. No starlight would reach the water. The ceiling would remain dark. Heat from below might create regions where the ice thins or fractures. Water could rise into cracks and freeze again, leaving layers that record earlier activity. If pressure builds beneath the shell, occasional eruptions might carry vapor or ice grains toward the surface. On a body moving through interstellar space, such plumes would be difficult to detect. There would be no nearby star to illuminate them. The material would reflect only the weak combined light of distant stars, unless the planet remained warm enough to glow in the infrared. Even an active surface could stay hidden from faraway telescopes. A moon around a rogue giant could offer another route to internal warmth. When moons orbit in resonant patterns, their gravitational pulls can keep one another's paths slightly eccentric. The distance from the planet changes during each orbit, causing the moon to flex. That flexing produces heat. In our own solar system, this process powers intense geology on some moons and helps maintain subsurface oceans on others. It does not depend on sunlight. If a giant planet is ejected while retaining several close moons, their resonances may survive. The system would become a small traveling family. The planet would provide gravity. The moons would pull on one another. Tides would continue beneath a sky with no central sun. A close moon could remain active long after the system entered interstellar space. Its ocean might be maintained more by orbital motion than by radioactive decay. The arrangement would not last forever unchanged. Tides exchange energy and angular momentum. Orbits can expand or contract over time. Resonances may weaken. Internal heating can decline, but for long intervals, the system could preserve conditions far warmer than its surroundings. This leads to a useful shift in perspective. We often describe a rogue planet by what it lacks: no star, no daylight, no ordinary year, no familiar seasons. From the outside, those absences define it. From the inside, other structures matter more. A molten or partly molten core, a convecting mantle, a layer of liquid beneath ice, a dense atmosphere trapping infrared radiation, a moon whose orbit continues to flex its interior. The world is not sustained by a single source of energy. It is shaped by several smaller sources, each fading at a different rate. Some of these planets may remain active for millions of years. Others may preserve liquid reservoirs for billions. The uncertainty is large because we have not observed a confirmed hidden ocean on a rogue planet. The idea comes from physical models and from comparisons with planets and moons closer to home. Those comparisons are valuable, but incomplete. A starless Earth mass planet would not simply be Earth with the sun removed. Its atmosphere might collapse. Carbon dioxide could freeze onto the surface. Nitrogen could condense under sufficiently cold conditions. Ocean circulation would stop near the top and continue only below the ice. A more massive planet could retain a deeper atmosphere. A hydrogen-rich atmosphere might prevent surface freezing for a time. High pressure could create temperatures suitable for liquid water. Even without stellar energy, the surface under such an atmosphere would not resemble an open sea beneath a clear sky. The air could be hundreds of times denser than Earth's. Clouds and haze might hide the stars. Heat would rise from below and become trapped before escaping into space. Rain, if it occurred, could be driven by internal energy. Winds might be slow or powerful depending on the atmosphere's depth, rotation, and heat transport. Without a day side and a night side, circulation would not follow the same pattern as weather on planets close to stars. There might be no morning, no afternoon, no familiar movement of warmth across the surface, only the rotation of the planet beneath a sky of distant light. For a listener resting on Earth, that kind of world can seem completely removed from experience. The physics holding it together is familiar. The ice in a glass slows the transfer of heat. A blanket reduces the rate at which warmth leaves the body. Rock deep beneath the ground remains warmer than winter air. Gravity holds an atmosphere close to a planet. At cosmic scales, these ordinary principles continue. A frozen shell becomes insulation. A dense atmosphere becomes a thermal barrier. A moon's orbit becomes a source of heat. A planet's interior becomes a memory of formation. That memory fades, but it may fade more slowly than the light of the lost star. And somewhere beneath kilometers of ice, an ocean may continue moving, long after the surface has forgotten what daylight was. A world moving alone through the galaxy does not move through perfect emptiness. Interstellar space contains thin gas, scattered dust, magnetic fields, high-energy particles, and light arriving from every direction. The density is extremely low by ordinary standards, but the journey of a rogue planet can last for billions of years. Over that span, even a sparse environment becomes part of the planet's history. Most of the time, the surrounding medium offers almost no resistance. A planet is too massive for interstellar gas to slow it in any meaningful way over a human lifetime. It continues along the orbit it follows around the center of the Milky Way, carrying the speed and direction produced by its earlier gravitational encounters. That path may be measured in tens of kilometers per second. At such speeds, the planet crosses the distance between Earth and the Sun in a matter of weeks. Yet the gaps between stars are so large that entire ages can pass without a close approach to another system. A rogue planet may travel for millions of years before passing within even a light year of a star. The galaxy is crowded only when viewed from very far away. From inside it, neighboring suns are widely separated islands. This makes the interstellar journey less like moving through a busy field and more like crossing a dark ocean whose lights remain near the horizon. Stars come closer in projection, then separate again. Their brightness changes slowly. The patterns of constellations shift as the planet moves through the galaxy. There is no permanent sky. From Earth, the stars appear nearly fixed because a human life is short compared with stellar motion. From a wandering planet, traveling for hundreds of millions of years, the geometry would continually unfold. Some stars would pass nearer and brighten, others would recede, new patterns would form, hold for a time, and dissolve. The Milky Way itself would remain a broad structure across the sky, though its exact shape would depend on the planet's location within the galactic disk. If the world moved above or below the main plane, the band of stars might appear more concentrated in one direction. The sky would carry motion without any local sun to dominate it. A nearby stellar passage could still matter. Most encounters would be too distant to alter the planet's path greatly, but the galaxy allows rare events. A rogue world could pass through the outer region of a planetary system, cross a stellar nursery, or move near a compact object. Each possibility changes the journey in a different way. A passing star can bend the planet's trajectory. If the encounter is distant, the deflection is slight. The planet leaves with almost the same speed, but on a somewhat different galactic path. A closer passage can exchange more energy. The star may accelerate the planet or slow it relative to the galaxy. In unusual circumstances, the planet could be captured. Capture is possible, but difficult. For one object to become permanently bound to another, energy must be removed from their relative motion. A simple encounter between one star and one planet usually changes direction without producing capture. The planet approaches, gravity accelerates it, it swings around the star. Then it departs with nearly the same speed it had before the encounter. To remain, the system generally needs another participant or another way to lose energy. A binary star can provide that complexity. As the rogue planet passes through the changing gravity of two stars, it may exchange energy with their orbit. One star can give the planet momentum, while the other removes it. In rare cases, the planet leaves the encounter bound to one or both stars. A planetary system can also act as a gravitational network. A rogue planet entering such a system may interact with an existing giant planet. Energy can pass between them, leaving one object more tightly bound and the other less so. The result could be capture. It could also be another ejection. A wandering world may enter a system and displace a planet that formed there, taking a new orbit while the original world is thrown outward. These events are expected to be uncommon, but they reveal that planetary identity is not always permanent. A planet can be born around one star, leave it, travel through interstellar space, and later become part of another system. Its new orbit might be wide, tilted, or strongly elliptical. Such unusual paths are among the clues astronomers look for when considering whether a planet may have been captured. Yet an eccentric orbit can form in many other ways, so orbital shape alone cannot prove an interstellar origin. A captured world may become nearly indistinguishable from a native planet. Over time, the system continues. Moons may adjust, rings may evolve, atmospheres respond to the new radiation. The earlier starless interval remains part of the planet's past, but little in its present appearance may reveal it. For a frozen rogue planet, capture could bring a second beginning. As the new star grows brighter in the sky, surface ices may warm, volatile materials can change phase, gases, frozen onto the ground, may return to the atmosphere. A buried ocean might respond more slowly. The upper ice shell would absorb heat from above, while geothermal energy continued from below. Cracks could form as different layers expand. Meltwater might appear near the surface. The result would depend on the new orbit. A distant capture could leave the planet mostly frozen. A closer orbit might produce extreme heating. An eccentric path could create long intervals of cold, interrupted by intense passages near the star. There is no guarantee of a stable, temperate world. Capture is a gravitational event, not a careful placement. The planet arrives with whatever speed and direction the encounter allows. In some cases, the new orbit might remain unstable. Further encounters could eject the planet again. A world could become rogue more than once. The galaxy has enough time for complex histories. A planet formed billions of years ago may have belonged to several gravitational arrangements. Its surface could preserve layers from different climates. Its moons might include companions acquired in separate eras. This is difficult to confirm observationally, but it is allowed by the physics of many body systems. The same gravity that removes worlds can rearrange them. A passage near a star also changes the planet before any capture is decided. Even an unbound flyby can provide a temporary season of light. For a few years, or perhaps only a few months, the distant sun grows larger and brighter. The planet enters a region where external heating becomes noticeable. Its upper atmosphere responds first. On a giant planet, clouds may change altitude, frozen compounds may evaporate, chemical reactions driven by ultraviolet light can begin in the upper layers. On a rocky body, surface frost may retreat from the warmest regions. A thin atmosphere may briefly thicken as gases are released, then the planet moves away. The star contracts into a point, the warmth declines. Newly released gases freeze or escape, and the world returns to its internal balance. Such encounters may leave marks. A surface could carry deposits formed during repeated passages through warmer regions. An atmosphere might contain molecules produced during a close stellar approach. Ice layers could preserve evidence of temperature changes separated by millions of years. Reading that record would require reaching the planet from a telescope light years away. Most of these details remain inaccessible. The interstellar medium leaves subtler effects. High-energy cosmic rays strike atmospheres and surfaces. Without the protection of a nearby star's magnetic bubble, a rogue planet is directly exposed to the broader particle environment of the galaxy. A strong planetary magnetic field could deflect some charged particles, A thick atmosphere could absorb many others. A moon or small rocky world with little atmosphere would receive more direct exposure. Over long periods, radiation can alter surface chemistry. It can break molecules apart and allow new ones to form. On icy surfaces, energetic particles may create oxidants or more complex compounds. The results depend on the original materials and the local radiation environment. Radiation is often described only as destructive, but chemically it is also a source of change. It moves molecules away from equilibrium. That movement can create stored chemical energy. Whether such chemistry could support life beneath an ice shell is uncertain. Surface products would need a path downward, perhaps through fractures, overturning, ice, impacts, or cycles of melting and freezing. If oxidized materials from the surface reached a chemically reduced ocean below, the difference between them could provide an energy gradient. The process is known in our own solar system as one possible way an icy moon might supply chemical fuel to its subsurface water. For a rogue planet, the same basic mechanism could operate without sunlight. Cosmic radiation would replace some of the chemical role played by a parent star. The energy input would be weaker than direct solar radiation in many settings, but it could continue for immense spans. Dust impacts add another layer. Interstellar grains are small, yet they strike at high relative speeds. Most burn or vaporize in an atmosphere. On an airless surface, they create tiny craters and melt small amounts of material. Larger, interstellar bodies are much rarer. A rogue planet could encounter comets, asteroids, or fragments that also move between stars. Impacts would be infrequent, but over billions of years, they could deliver new compounds or excavate deeper layers. A collision with a large object could alter rotation, atmosphere, or satellite systems. The odds are low for any single journey. The available time is not. Even so, most wandering worlds probably spend nearly all their existence undisturbed. Their main evolution comes from within. The core cools, the mantle convects more slowly. Magnetic fields weaken or reorganize, atmospheres contract and condense, cloud decks descend, moons migrate, ice thickens. The surrounding galaxy changes far more than the planet's immediate sky suggests. Stars are born in distant clouds. Others age and die. Spiral patterns shift. The planet continues around the galactic center, completing orbit after orbit without a local year. A galactic year lasts hundreds of millions of Earth years. During one such circuit, a rogue planet may pass through regions of denser gas, near spiral arms, and into quieter stretches between them. Its environment changes, though never with the regularity of seasons around a star. There may be intervals when nearby supernovae raise the local radiation level. There may be long passages through regions with few bright stars. The planet's age could exceed the present form of entire constellations. If it began near a star cluster, that cluster may disperse until its siblings are spread across a large part of the galaxy. The parent star may no longer be identifiable. The planet becomes separated not only by distance, but by lost context. Its origin remains real, though no observer may ever reconstruct it. This is one reason rogue planets are important to planetary science. They are not merely isolated objects. They are evidence of what planetary systems can lose. Every one implies a history of formation, interaction, and motion. Their abundance carries information about how often young systems become unstable, how many worlds are formed, and how frequently those worlds are expelled. To count wandering planets is to measure the untidiness of planetary birth. It is also to recognize that the galaxy may contain more planetary stories than visible stars can reveal. A solar system shows us the worlds that stayed. Interstellar space holds some of the worlds that did not. And between those two populations lies a fuller record of how planetary systems change. The first rogue planet was not discovered as a complete world. It appeared as an event. A background star brightened. The signal lasted for a limited time. A model suggested the mass of the unseen lens. Then the alignment ended, leaving astronomers with a trace of light and a range of possible explanations. That pattern has shaped the study of wandering planets ever since. To understand how many of these worlds exist, researchers cannot simply count a collection of visible objects. They must begin with rare detections and work backward toward the much larger population that produced them. This requires statistics. A survey may monitor millions of stars and record only a small number of very short microlensing events. Each event has a different probability of being detected. Some occur while a telescope is not observing. Some are lost to weather. Some happen spun in fields where stars overlap too densely for precise measurements. Others are too weak or too brief to rise above the noise. The events that appear in the final sample are therefore not a direct census. They are the visible portion of a selection process. Astronomers must estimate what the survey would have missed. They insert simulated lensing signals into real observations and test whether the detection software can recover them. A bright, long event may be found almost every time. A faint event lasting only a few hours may be recognized far less often. This recovery rate becomes part of the calculation. If a survey finds one event of a type, it could detect only 10% of the time. That single observation suggests a larger underlying population than an event the survey would detect nearly always. The same reasoning applies across mass. Jupiter mass rogue planets create stronger, longer lensing signals than Earth mass worlds. They are easier to notice. Smaller planets may be far more numerous, while producing fewer confirmed detections. A census that ignores this difference would make the galaxy appear weighted toward large worlds. Simply because large worlds are easier to find, distance also matters. A lensing planet may lie nearby or thousands of light years away. Its probability of creating a measurable alignment depends on how much space it occupies between Earth and the crowded field of background stars. The motion of the planet matters too. A fast lens crosses the alignment quickly. A slower one produces a longer event. Two planets with the same mass can therefore leave different traces. The final population estimate is assembled from many interacting uncertainties. How often did the telescope observe? How sensitive was it at each moment? How crowded was the field? How faint was the source star? How fast was the lens moving? How far away was it? And how well could a short event be distinguished from every other form of variability? Small changes in the assumptions can shift the answer. This is why estimates of rogue planet abundance have varied. Some early studies suggested that Jupiter's mass wanderers might be common enough to rival the number of ordinary stars. Later analyses, using larger data sets and improved treatment of short events, often pointed toward fewer isolated giants. The broad conclusion remained: free-floating planets exist. The precise number at each mass is still being refined. That uncertainty is not a failure of the method. It is a measure of how difficult the population is to observe. The galaxy has not placed these worlds in a convenient catalogue. It reveals them through brief alignments scattered across years of data. The most important number may not be the total number of rogue planets. It may be the shape of their mass distribution. If astronomers find many Jupiter mass objects, that would suggest that young systems often eject giant planets, or that star-like collapse produces large numbers of isolated bodies in the same mass range. If smaller worlds dominate, the picture changes. Rocky planets and icy bodies are easier to scatter than giants, because a close encounter with a massive neighbor can remove them without requiring another planet of similar size. Young systems may create many such objects and lose them before they become stable. The population could therefore rise toward lower masses. There may be more Mars mass wanderers than Jupiter mass wanderers. There may be more Moon mass bodies than either. At some point, the meaning of planet begins to blur into the wider population of interstellar objects. A body the size of Earth is comfortably planetary. A body the size of Pluto may be called a dwarf planet if it orbits a star. But in interstellar space, the same label becomes less useful. Smaller still are free-floating asteroids, comets, and fragments. The galaxy may contain a continuous range of solid bodies, from gas giants down to stones, all moving without permanent attachment to a star. The distinction between a rogue planet and an interstellar minor body is partly physical and partly historical. A large object can hold itself in a rounded shape through gravity. It may possess differentiated layers, an atmosphere, or internal geology. A smaller fragment may preserve the irregular shape of a collision, but both may have been expelled by the same process. A giant planet scatters a rocky world. That rocky world disturbs a belt of smaller objects. A passing star loosens comets from the distant edge of the system. One period of instability can fill interstellar space with bodies spanning many orders of magnitude in mass. The few interstellar objects observed passing through our own solar system belong to this wider picture. They demonstrate that material can move from one stellar system into another, though the known examples are far smaller than planets. Their discovery was possible because they approached the sun. Sunlight illuminated them. Their motion revealed that they were not gravitationally bound to our system. A rogue planet passing nearby would be more dramatic in mass, but not necessarily easier to see. Without reflected sunlight or sufficient internal heat, it could remain hidden until its gravity affected something observable. A close passage is possible. The Milky Way has existed long enough for many wandering worlds to cross the regions between stars. Yet, the distances are so large that a rogue planet entering the inner solar system would be a rare event. Most pass far away. They may move through the distant outskirts, beyond the major planets, producing only small gravitational effects. A sufficiently massive object could disturb comets or alter the paths of remote bodies, but separating such influences from the many other sources of orbital change would be difficult. There is no good evidence that an unknown rogue planet is currently approaching the inner solar system. The possibility belongs to celestial mechanics, not to prediction. Its value is not in alarm, it is in scale. Even if the galaxy contains billions of wandering worlds, space between stars remains wide enough that most of them never come close to us. A large population does not mean a crowded local environment. It means an immense volume containing an immense number of isolated paths. To picture this, imagine distributing a handful of grains across an empty room. Each grain is easy to miss, even though the total number is not small. Now expand the room until the distance between grains is measured in light years. The Milky Way can hold vast populations while leaving most objects separated by distances that make encounters uncommon. This is one reason population estimates are so important. Individual detections tell us that rogue planets exist. The distribution tells us how planetary systems behave. A galaxy rich in ejected Earth mass worlds would imply that the formation of rocky planets is highly efficient, even if many do not remain in stable orbits. A galaxy rich in isolated giants might indicate frequent instability among young massive planets, or a star formation process that extends smoothly into planetary masses. A shortage of certain worlds would also carry meaning. If very few large, rogue planets are found, giant planets may usually remain bound or be too uncommon to supply a large wandering population. If small worlds are abundant, the apparent order of mature planetary systems may conceal a much more violent beginning. The planets we observe around stable stars would then be survivors. Their nearly regular orbits would not show how many companions were removed before the system reached its present form. Our own solar system may also have lost material during its youth. Models of its early evolution often include migration among the giant planets and the scattering of smaller bodies. Whether any full-sized planet was ejected remains uncertain, though some scenarios allow that possibility. What is clear is that the architecture we see today need not match the architecture that first formed. Planetary systems evolve, orbits shift, bodies collide. Worlds exchange energy, some remain, some leave. The rogue population preserves the leaving side of that history. A mature solar system is like a room after the furniture has been arranged. The empty spaces do not reveal how many objects were moved out, broken, or carried away during the process. Interstellar planets are part of what was carried away. Their abundance may eventually help astronomers compare different birth environments. Stars formed in dense clusters experience more nearby gravitational encounters than stars formed in looser groups. Systems with several giant planets may eject more worlds than systems with only small planets. Binary stars may create different patterns of stability from single stars. If rogue planets can be connected statistically to stellar populations, they may reveal where ejection happens most efficiently. Young planetary mass objects near star-forming regions provide another kind of evidence. Their ages can sometimes be estimated from the surrounding stellar population. Their motions can show whether they belong to the same association. Yet their origins may remain uncertain. Some could be embryos expelled from disks. Others could be the smallest products of cloud collapse. The ratio between these groups would help define where planet formation ends and star formation begins. Nature may not honor that boundary as sharply as language does. A cloud can fragment into objects of many masses. A disk can build bodies approaching the lower range of brown dwarfs. Ejection can remove planets before they finish growing. The result is an overlapping population whose present appearance does not always preserve its birth mechanism. The census must therefore use more than one method. Microlensing is sensitive to gravity, including cold old planets that emit almost nothing. Infrared surveys are sensitive to warmth, favoring young or massive bodies. Astrometry can reveal subtle changes in position. Deep imaging can search nearby stellar nurseries. Spectroscopy can compare atmospheric chemistry and surface gravity. Each method sees a different portion of the same hidden population. When their results are combined, a fuller map begins to appear. It is not a map of locations in the ordinary sense. Most detected microlensing planets will not remain available for detailed follow-up. Instead, it is a map of probabilities, how many worlds exist at each mass, how their speeds are distributed, how frequently they are young or old, how often they belong to stellar groups, how many are truly unbound, how many occupy very wide orbits that only appear isolated. For now, parts of that map remain faint. The number of known candidates is small compared with the population being inferred. The lower mass end is especially uncertain. Yet, every improvement in observing cadence and precision opens another part of the distribution. A survey that checks the same stars several times per hour can recover events missed by a survey that returns once per night. A space telescope avoids clouds and atmospheric blurring. Simultaneous observations from widely separated locations can measure parallax and narrow the range of possible masses. The science advances through patience and repetition, even though each individual event does not repeat. Millions of stars are measured again. Another brief brightening appears. Its curve is fitted. Its alternatives are tested. One more unseen object is added, not always as a named world, but as evidence within a growing population. The planets continue moving while the census slowly catches up. Some are warm enough to be photographed. Some are known only through a few hours of magnified starlight. Many more pass without any alignment at all. They remain part of the galaxy's planetary history, whether or not a telescope ever notices them, but even an unfinished count has changed the picture. A galaxy is no longer only a collection of stars and the planets held close to them. It also contains the worlds released into the spaces between. The next generation of surveys will search for wandering planets with a steadier rhythm. Microlensing has always depended on patience, but future observations are being designed to reduce the gaps that make short events so easy to miss. A planet with a mass near Earth may brighten a background star for only a small part of a day. To capture that rise and fall clearly, a telescope must return to the same crowded fields again and again, measuring millions of stars with consistent precision from the ground. This work is limited by the turning Earth. Daylight interrupts every observing site. Weather removes nights without warning. The atmosphere blurs starlight and changes from one exposure to the next. Networks of telescopes can reduce these interruptions, but they cannot remove them completely. A space observatory offers a different kind of continuity. Above the atmosphere, the stars do not shimmer. The instrument can maintain a stable view, and its measurements are not lost to clouds. Wide fields can be monitored at a cadence chosen for the events astronomers expect to find. This matters most for the smallest lenses. A Jupiter mass wanderer leaves time for several observatories to respond. A much smaller world may complete most of its lensing event before an alert can be issued. The signal must be found in the survey itself, already recorded with enough detail to reconstruct what happened. In the coming years, large microlensing programs are expected to expand the sample of free-floating planet candidates. Among the most important goals is measuring how the population changes from giant planets down toward worlds with masses closer to Earth. That lower range carries much of the scientific value. Giant planets are difficult to eject, but their gravity can eject many smaller bodies. If young systems often contain several rocky worlds and planetary embryos, gravitational scattering may send large numbers into interstellar space. A survey sensitive to short events can test this idea. It may reveal whether the Milky Way contains a modest population of isolated giants and a much larger population of small frozen worlds, or it may find that the expected rise toward lower masses is weaker than current models suggest. Either result would reshape our understanding of planetary formation. A large number of Earth mass rogues would mean that many planets are built but never appear in the mature systems. Astronomers study around stars. The apparent architecture of those systems would represent only what remained after a long period of sorting. A smaller number would suggest that ejection is less efficient, that rocky planets are harder to form in abundance, or that many short events have origins that current models do not capture correctly. The measurements must be careful because a brief lensing signal carries limited information. To estimate mass more directly, astronomers can observe the same event from two separated locations. Earth and a spacecraft do not see the alignment from exactly the same angle. The difference may slightly change the timing or height of the brightening. This microlensing parallax provides another piece of the geometry. Combined with an estimate of the angular lensing scale, it can narrow the range of possible masses and distances. For some events, the uncertainty that once separated a low-mass nearby object from a more massive distant one can be greatly reduced. Not every event will provide all the required measurements. Some background stars are too faint, some alignments are not close enough, some signals are too short or poorly sampled. But a large survey does not need perfection in every case. It needs enough well-measured events to reveal the population as a whole. Direct imaging will continue to work from the opposite side of the problem. Instead of detecting gravity, it detects heat. Sensitive infrared telescopes can search nearby young associations for objects too faint to be stars. As instruments improve, They can reach lower temperatures and smaller masses. Spectroscopy then separates their light into chemical patterns. Water vapor, methane, ammonia, carbon monoxide, clouds, and pressure-dependent features can help describe the atmosphere. Surface gravity leaves its own imprint, offering clues to whether the object is young and inflated or older and more compact. These observations may not reveal whether an isolated body formed inside a disk or from a collapsing cloud, but they provide the detailed physical portrait that microlensing usually cannot. The two methods complement one another. Microlensing finds old cold objects across large distances, often with little atmospheric information. Infrared imaging studies warmer nearby objects in greater detail. While missing most of the colder population, together they begin to connect abundance with physical character. A future survey may show that small rogue planets are common. A nearby infrared discovery may reveal how a young one cools. A spectrum may show thick clouds or unusual chemistry. A moving group may provide an age. A later dynamical model may suggest whether ejection from a young system was likely. No single observation restores the entire history, but several kinds of evidence can bring parts of it into focus. There is also the possibility of detecting moons. A moon orbiting a free-floating planet may create a secondary feature in a microlensing light curve. The signal would be subtle and dependent on the geometry of the event. But in principle, the gravitational pattern of a planet-moon system differs from that of a single isolated lens. Finding such a pair would matter for more than classification. It would show that at least some planetary systems can survive ejection in miniature. The star may be lost while the local arrangement remains. A giant world and its close moons could continue together, carrying tides, resonances, eclipses, and internal heating into interstellar space. Rings may also survive, though they would be much harder to detect. Dusty disks around very young planetary mass objects can sometimes be observed in the infrared, suggesting that isolated bodies may retain material from formation. Some of that material could gather into moons. A free-floating object formed alone might therefore develop a small system around itself, even without ever orbiting a star. The distinction between a planet and a tiny planetary system becomes less clear. A central body provides gravity, material circles it, collisions shape the disk, satellites form. Light from a star is not required for the architecture to exist. It is only required for us to see much of it easily. Other techniques may eventually reveal wandering worlds closer to the solar system. Astrometric surveys measure the positions and motions of stars with great precision. A massive unseen object passing in front of a background star can shift its apparent position as well as its brightness. This astrometric lensing unfolds over a longer interval than the peak of the photometric event. In favorable cases, it can help determine the lens mass and track its movement after the main brightening has ended. For nearby objects, deep infrared observations may also detect faint thermal emission. A cold rogue giant at a relatively small distance could move noticeably against the background stars over months or years. Its proper motion would distinguish it from more distant sources. Smaller, rocky planets would remain much harder. A world the mass of Earth, old and far from any star, may emit so little energy that direct detection is beyond foreseeable instruments. Unless it passes unusually close, its gravity may still reveal it. This is one of the enduring strengths of microlensing. It does not ask whether a planet is bright enough. It asks whether the geometry of the galaxy will briefly place a distant star behind it. The answer is rarely yes for any one object. Across millions of stars and years of observation, rare alignments become a method. There is a calm persistence in that strategy. The sky is measured, not because every night contains a discovery, but because enough nights eventually contain the right arrangement. A distant star brightens for 3 hours, A computer marks the change. Other causes are removed. The remaining curve points toward a world that may never be seen again. Then the survey continues. The great advance will not come from one dramatic planet. It will come from a distribution, a set of masses, a range of speeds, a comparison between young clusters and old galactic fields, a better distinction between unbound planets and worlds in distant orbits, a clearer view of how often moons remain attached. The population will gradually become less hypothetical. Its members may still be unnamed and invisible, but their collective shape will emerge. That shape will tell us how common stability really is. Every planetary system begins in motion. The planets that remain near their stars can make the final arrangement appear inevitable. Circular paths and long-lived resonances give the impression of design. Rogue planets offer the missing correction. They show that formation is also loss. A system can build more worlds than it keeps. A planet can be complete and still be removed. A moon can continue circling after the sun has become a distant star. The surveys now being prepared will not return these worlds to their origins. They will do something quieter. They will place them back into the history of planetary systems where they have always belonged. A rogue planet has no final destination. It does not move toward a chosen star or wait for another system to receive it. Its path is simply the path gravity has given it, curving through the Milky Way as the galaxy itself turns. From far away, that motion may look lonely, but loneliness is a human word. The planet is not aware of absence. It does not compare its present sky with the one it once had. Rock cools, gas circulates, ice thickens. Moons continue in orbit. Heat rises through layers that may never again be touched by sunlight. The world remains physical. That simple fact matters. A planet does not stop being a planet when its star is gone. Its gravity still shapes it into a sphere. Its interior still holds a record of formation. Its atmosphere, if one remains, still follows pressure and temperature. Its surface still receives impact. Its magnetic field, if it has one, still reaches into surrounding space. Only the larger arrangement has changed. The world once belonged to a system defined by a central sun. Now, it belongs to the galaxy more directly. Its year is no longer measured by a stellar orbit. Its deeper motion is the long circuit around the center of the Milky Way. During that journey, the planet may pass through several spiral arms. It may travel near regions where stars are forming, then spend ages in thinner parts of the galactic disk. The constellations above it will change beyond recognition. Some stars that once surrounded it will die. Others will be born. The planet may continue through all of it. There is a scale of time at which even the loss of a sun becomes one event among many. A young world is scattered. Its surface freezes. Its atmosphere contracts. Its interior cools. A moon moves slightly farther away. A magnetic field weakens. Millions of years pass between each noticeable change. From the outside, almost nothing seems to happen. From within, the history continues. The same is true of the planetary systems that remain around stars. They appear stable because we observe them during a narrow interval. Yet every system carries the possibility of change. Orbits evolve, stars lose mass, passing objects disturb distant regions. Worlds exchange energy over spans much longer than recorded history. Rogue planets make that change visible. They are not exceptions to planetary formation. They are one of its outcomes. Their existence suggests that building a system is not only a process of accumulation, it is also a process of removal. Some material falls into the star. Some becomes moons. Some becomes planets. Some collides. Some is broken apart. Some is sent beyond the system entirely. The mature planets that remain are only part of the result. Between the stars are the rest of the stories. A gas giant may still carry storms driven by internal heat. A rocky world may preserve an ocean beneath ice. A moon may continue to flex under the pull of a planet that no longer circles any sun. A smaller body may freeze until almost every process at its surface has stopped. The range is wider than one image can hold. There is no single rogue planet. There are newborn ones glowing in infrared light. There are old ones detectable only through gravity. There may be worlds still accompanied by moons. There may be worlds stripped of everything but their own mass. Some may have formed alone. Others may remember in the chemistry of their atmospheres or the scars of their surfaces, the systems that released them. Most of those memories will never be read. A telescope may record a short microlensing curve and reveal only a mass estimate. An infrared spectrum may show water vapor and methane while leaving the origin uncertain. A faint moving point may be observed for years without ever exposing the path that brought it into isolation. Science often works with incomplete histories. The evidence does not become worthless because it is partial. A few hours of altered starlight can reveal that an unseen world crossed the line of sight. A faint infrared source can show that a planetary mass object is still warm. A population of brief events can reveal how often planetary systems lose what they create. Each observation adds one more piece to a larger pattern. The pattern is not finished. It may take decades of surveys to measure the abundance of Earth mass rogue planets. It may take longer to distinguish ejected worlds from objects that formed alone. Some questions may remain difficult even when the number of detections grows. But the direction is clear. The spaces between stars contain structure. They contain history. They contain worlds. For most of human experience, planets were lights that moved across the sky. Later, they became nearby places orbiting the sun. Then came planets around other stars, first inferred and eventually counted by the thousands. Now, the category has widened again. A planet does not require visible attachment. It can exist between systems, unseen and unilluminated, while remaining as real as any world, circling a bright star. This changes the mental map of the galaxy. The Milky Way is not only a field of suns with planets gathered close around them. It is also crossed by objects moving through the intervals, carrying the consequences of old gravitational encounters. Some are too cold to see. Some are too small to detect. Some will never align with a background star while any telescope is watching. They will continue without being counted. The lack of observation does not reduce their existence. Far from Earth, one such planet may be rotating now. Its surface may be covered in ice older than many stars visible from our sky. Beneath that ice, rock may still release heat. Above it, the Milky Way may stretch across a sky with no bright center. The planet is not waiting. It is not lost in the sense that a traveler is lost. There is no route it failed to follow. There is only motion. A long curve through the galaxy. A remaining supply of internal energy. A history written in layers. And a future shaped by encounters that may never come. On Earth, night arrives because our planet turns away from the sun. Morning returns because the rotation continues. For a rogue planet, there is no morning in that familiar sense, but there is still change. Clouds shift, ice settles, moons rise, stars move across the sky. Gravity continues its work. The planet carries no sunrise, yet it carries everything it has become. And somewhere between the stars, a frozen world keeps turning.